Okay, so last class we were just kind of ending or beginning a conversation on the quantum internet, and the key technology that is enabling the quantum internet is quantum key distribution. And so in quantum key distribution, you have two distant users. Usually in quantum information science, they're called Alice and Bob, so they are here. And they're going to exchange qubits through some quantum channel. And with a proper protocol, we'll give an example of one in a second, quantum theory ensures that any attempt to eavesdrop on this quantum channel results in modification of the qubits, which Alice and Bob will be able to detect during some kind of processing stage. The processing stage might be a phone call, for example. So quantum key distribution offers a secure way to exchange these cryptographic keys between locations. And the main limitation of this scheme is that the qubit signals cannot be amplified. So that means that these quantum key distribution links are limited in distance. And so commercial systems that have been kind of put out there are pretty short range, over about 100 kilometers. And sort of examples in academic settings have managed several hundred kilometers. So the security of quantum cryptography rests on a couple key principles listed here. So Heisenberg's uncertainty principle, the no cloning theorem, and entanglement. So if we start with the Heisenberg uncertainty principle, when Heisenberg originally put forward this idea, he said that only one property of a pair of conjugate properties can be known with certainty. And in his case, he was talking about the position and momentum of a particle. For quantum cryptography, we can leverage this idea, but we're usually using the polarization state of a photon as our conjugate properties. And the reason that we choose the polarization state as our conjugate properties is because photons can be exchanged over our fiber optic networks that we were talking about in our sort of idea of quantum internet. And maybe the most practical quantum systems for transmission between two parties that wish to exchange some information between the two. So light is going to make quantum communication possible. So the qubit technologies that are being considered in this kind of application are pretty much only photonic qubits or photons. So principle of quantum mechanics, the no cloning theorem kind of follows naturally from the uncertainty principle in this idea of quantum key distribution. So what it says is that it's impossible to create identical copies of an arbitrary, unknown quantum state. So why is that important? That's important because without the no cloning theorem, it would be possible to circumvent the uncertainty principle by creating multiple copies of your quantum state and measuring the different conjugate properties on the different copies that you made. So this would allow you to simultaneously know with certainty both conjugate properties of the original qubit that you sent out, and that would be a violation of the Heisenberg uncertainty principle. So no cloning theorem keeps us in check. And then the last big principle of quantum mechanics that we have to consider is entanglement. So it's possible for two particles to become entangled such that when a particular property is measured in one particle, the opposite state or some other connected state will be observed on the entangled particle instantaneously, no matter how far apart the two particles are in space. It's impossible to predict, though, prior to measurement, what state will be observed, and so it's not possible to communicate through entangled particles without discussing your observations through some kind of classical channel, like on the phone. So the process of communicating using these entangled states, aided by a classical channel, is also known as quantum teleportation. So let's look at a specific example of what one of these quantum key distribution protocols look like, because in theory, sounds great, sounds pretty straightforward, but what does this actually look like in practice? All right, so the protocol that we're going to talk about is called the BB84 protocol. This stands for two persons' names, Charles Bennett and Gilles Brassard. They kind of developed this in 1984, and it's the first quantum cryptography protocol. What we're going to do is we're going to define our bit in the polarization state of a photon. And the polarization state can be in two different bases. So we can have our binary 1 in a 90-degree rectilinear basis, and our binary 0 in that same 90-degree basis. Or we can have, so this is the rectilinear basis, or we can have our binary 0 at 45 degrees, and our binary 1 at 135 degrees in our diagonal basis. A bit can be represented by polarizing a photon in one of these two bases, and I can choose what basis I use. So in the first phase of this protocol, Alice is going to communicate with Bob over the quantum channel. She's going to begin by choosing a random string of bits. So Alice, she chooses a random string of bits, and for each bit, she's going to randomly choose a basis. But she knows what basis she's choosing. So rectilinear or diagonal, on which to encode, by which to encode the bit. So she's going to transmit a photon for each bit with the corresponding polarization as described to Bob. For every photon Bob receives, he's going to measure the photon's polarization. So he's going to measure the photon's polarization using a randomly chosen basis. And if for a particular photon Bob happens to choose the same basis as Alice, then in principle, Bob should measure the same polarization, and so he can correctly infer that Alice, he can correctly infer the bit that Alice was intending to send. If he chose wrong, his result, and thus the bit he reads, is going to be random. All right, so that's phase 1 of our protocol. So in phase 2, Bob is going to notify Alice over some insecure channel, so he calls her up, what basis he used to measure each photon. So Alice is going to report back to Bob whether he chose the correct basis or not. So at this point, Alice and Bob are going to discard the bits corresponding to photons which Bob measured in a different basis. All right, so provided no errors occurred and no one manipulated the photons, Bob and Alice should now have an identical string of bits, and that identical string of bits is called the sifted key. All right, so let me show you an example of what this looks like. All right, so I'm going to make a table. So here's Alice's bit, and then her basis, her polarization, and then Bob's basis, Bob's measurement. All right, so Alice's string of bits is 0, 1, 1, 0, 1, 0, 0, 1. And the basis she chose at random is, I'm going to do plus for rectilinear and an x for the diagonal. So plus, x, plus, x, 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 plus. And then the polarization. The polarization is up 90 degrees, 135 degrees, up 135, 45, 45. Right. Okay. Now Bob's basis is plus x, 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 plus x, plus plus. All right, and then he does his measurement, and this is what he gets. He gets up 45, 135, 45, right, 45, right, right. Okay, so now they have their phone call conversation. They compare notes. And the ones where Bob picked the right basis to do his measurement should match. And so their sifted key comes out to be 0, 1, 0, and 1. So the ones where they match. All right, so before they're finished, Alice and Bob agree on a random subset of the bits to compare. So they haven't told each other these numbers yet. But now they're gonna check their work. And so they're gonna say, okay, we're gonna check, bits 1, 4, and 5. They check them. And if the bits agree, they're thrown away because they're not secure anymore. And they'll keep the remaining bits in their sifted key to be their cryptographic key. In the absence of noise or any other measurement error, a disagreement in any of the bits compared would indicate the presence of an eavesdropper on the quantum channel. And that's because the eavesdropper, we call her Eve, if she were attempting to determine the key, she would have no choice but to measure the photons that were sent by Alice before further sending them on to Bob. And this would be true because the no cloning theorem tells us that she can't just reproduce them. She actually has to measure them. So since Eve will not know what basis Alice used to encode the bits until after Alice and Bob have their public non-secure discussion, Eve will be forced to guess. And so if she measures the incorrect basis, the Heisenberg uncertainty principle ensures that the information encoded in the other basis is now lost. So when the photon reaches Bob, his measurement will now be random, and he'll read a bit incorrectly 50% of the time. And given that Eve will choose the measurement basis incorrectly 50% of the time, because there's two choices, 25% of Bob's measurements are going to differ from Alice. And so if Eve has eavesdropped on all the bits, then after n bit comparisons by Alice and Bob, they'll reduce the probability that Eve will go undetected to 3/4 raised to the n. So the probability of Eve going undetected, just based on Heisenberg uncertainty principle and the fact that she has to measure the photons, is 3⁴ raised to the n, where n is the number of bits. And so if I'm talking about a string of 1,000 bits, so we're not talking about 10, we're talking about lots of bits here, then 3⁴ raised to the 1,000th, that's like, for n equals 1,000, that's like 10 to the minus 125. So there's no chance she won't be detected. So the security of quantum key distribution relies on this fact that Eve has to make a measurement in order to eavesdrop on the quantum channel. And the measurement will impact the outcome. All right, so the first practical implementations of quantum key distribution were offered to medium-scale companies who needed secure links between two distant buildings. Think like regional data centers or something like that. And the links were only point-to-point. And the end users had to know and operate their own system, which restricts the scope of use a lot. So longer distances and more complex topologies are really what's needed to make this a reality. And so that's where we go from the idea of point-to-point quantum key distribution to the idea of a quantum network that combines multiple quantum key distribution links into a single network. And users at any node of the quantum network can ask the quantum network to build end-to-end secure keys. So the nodes in the quantum network, we call them trusted nodes, combine the secret keys from different quantum key distribution links, and those nodes and operators are required to be trusted by the end users. So there is some fallibility in the system because the trusted nodes really do have to be secure. But that's the idea for how this is going to be put together. So today, all the existing quantum networks that are out there, small scale, rely on these trusted node architectures. And these are kind of growing really rapidly. So right now, there's a quantum network extending thousands of kilometers across hundreds of nodes in China. And there's a countrywide quantum network being built in South Korea. And through collaboration in the European Union, they're also planning a quantum communication infrastructure, which is going to include both ground-based and space-based quantum key distribution links. So this stuff is here, it's happening. BB84 is just like one example of a quantum key distribution protocol. There are many others. I like this one because it's really simple to understand just using simple polarization readout. But a lot of the other ones are pretty similar as well. So a major hurdle in the widespread adoption of quantum key distribution is this need for trusted nodes. And ideally, that would be eliminated if quantum repeaters are developed. So quantum repeaters are relays that amplify the signals from the starting sites, and they're going to be able to transfer the qubit information without measuring the qubits. So once we have quantum repeaters, we don't need trusted nodes anymore, which is how it's operating now, and we can kind of go to town in a secure way. So in quantum networks, the quantum layer is only used for the transport of qubits, and the end product provided by the network are classical keys, like we just saw here. The next step is to go to full quantum and keep all the exchanges at the quantum level. So don't have a classical channel readout in this discussion. And at this point, quantum networks wouldn't exchange keys, but rather exchange entangled states of photons. That's starting now at the local and regional level, but could lead to completely new type of quantum internet in the future. But that's definitely a further term goal. So just like the classical internet, when it was first created, I don't think people knew what it was going to be used for. That's also true of the quantum internet. People don't really know what it's going to be used for. I mean, security is one thing, but I think there's lots of possibilities. And as quantum computers get fed into this, I think the possibilities are going to be really pretty extensive. We're going to talk a little bit about just some basic principles of the different qubit platforms that underlie these quantum technologies. And so we just talked a lot about photons, and clearly the polarization state of photons is a type of qubit. We'll also talk a little bit about superconducting qubits, which we introduced via Josephson junctions a bit. We'll talk about trapped ions and spin qubits. We talked a little bit about spin qubits already when we mentioned NV centers. And I'll mention a little bit on topological qubits. So just as a reminder, all of these qubit technologies are sort of being pursued to differing extents by different companies. So superconducting qubits by far is kind of the biggest, most advanced in terms of commercial development. So Rigetti, IBM, D-Wave, Intel, several other companies are developing superconducting systems. So the quantum supremacy discussion we had earlier, the 50 to 70 qubit systems made by Google, those are in the superconducting family. Then trapped ions, photons, neutral atoms, silicon, and etc. All right, so superconducting qubits rely on superconducting electronics, Josephson junctions like we described. And these things are interesting because to maintain coherence, it's essential to keep electron-electron interactions and also interactions between electrons and other degrees of freedom, like phonons, for example, in the solid, under control. So coherence requires minimizing interactions with the environment. And superconductings have a huge advantage in this regard because the superfluid that's created in a superconductor as a result of formation of Cooper pairs is able to move through the material without any resistance. That means without any interactions with its environment. So just really briefly, the way I think about a Cooper pair as an experimental chemist is when you have an electron in a lattice, the positively charged ions that make up the lattice will be attracted to that electron. So there's a region of local positive charge that's built up as the electron is moving through the material. And that region of positive charge can actually attract a second electron. And under the right scenario, those two electrons can condense into a single object called a Cooper pair. And that's the base, and they now move as a single object in the superconductor. So that's kind of what's shown in that diagram. So the behavior of the electron superfluid is completely determined by a single quantum wave function. The amplitude of the wave function determines the number of Cooper pairs, and the value of the phase is related to the supercurrent in any magnetic field that's present in the material. So the amplitude and phase of the wave function are the two conjugate variables here. So they're related by the uncertainty principle, meaning we can't measure them at the same time with arbitrary precision anyways. And there's two primary types of superconducting qubits. One is called a charge qubit, and one is called a flux qubit. And the charge qubit, they're associated with the amplitude of the wave function, and the flux qubit is associated with the phase. And as I mentioned when we introduced Swift magnetometers last class, the key component in all these superconducting qubits is the Josephson junction, which is shown in the bottom left there. So that's just thin layer of aluminum oxide. That's our buffer layer in between two superconducting regions. And when the superconductor is cooled really low in temperature, the insulating layer is so thin that the Cooper pairs can tunnel through it and couple the superconducting wave functions on either side of the barrier. And so most of the circuits for superconducting qubits built so far consist of these junctions and other components like capacitors connected by superconducting leads. You can see kind of a schematic of what one of these looks like there, and a real picture of what a few of them, set of four, looks like in the picture there. And so, like I mentioned, lots of folks are working on these, and the big advantage is this resistanceless flow of charge, meaning that there's very little interactions with the environment. These electronics work very fast, and they're built on existing semiconductor industry technologies. The issue is they have to be kept very cold using dilution refrigerators at like 1.2 Kelvin. So not just cold, very cold. And if not, they collapse really easily. All right, let's talk about trapped ions. So trapped ions use internal electronic states of the ion for the qubit states, the 0 and the 1. So you can see sort of a representative, really crude schematic in the diagram on the right. And there are 4 types of states that you can kind of create out of trapped ions. You can create hyperfine qubits. And here the qubit states are hyperfine states of the ion separated by an energy splitting of gigahertz. You can also look at Zeeman qubits. And here the qubit states are magnetic sublevels split by an applied field. And they typically have megahertz frequencies. You can have fine structure qubits, where the qubit states reside in the fine structure levels and are separated by terahertz. And then last of all, you can have optical qubits, where the qubit states are separated by optical transitions, typically hundreds of terahertz. So initialization and readout in trapped ions are both performed by laser manipulation, like you can see in the diagrams here, of the ion internal and motional states. So initialization is performed via optical pumping into the excited state. That's our 1 state. And that's often accompanied by cooling of the ion's quantized motion to the trapped harmonic oscillator. So you have your ion, it's in a trap. The trap is defined by some harmonic oscillator, and you cool you're cooling the ion down in that potential well. State readout is likewise pretty darn simple. A resonant laser couples the one state to a cycling transition that scatters many photons that can be collected by a detector. And what's nice about this is that no similar transition exists for the zero state, so that remains dark. So you get really high fidelity state preparation and readout in fast timescales because you're doing this with lasers. So typically less than 1 millisecond. So the advantages of trapped ion qubits is that they have coherence times that can be really long for all four of these types of qubits. The hyperfine qubit coherence times have been measured as high as 50 seconds without using any kind of spin echo or other dynamic decoupling protocols. And with that kind of dynamic decoupling, they've gone up to like 600 seconds, so super long. And these coherence times are effectively T2 times. We'll learn all about T1, T2, et cetera, later in the course. These are sort of dephasing times. They define the probability that a qubit will stay in the excited state, the one state, at a given time after initialization. And those dephasing times are limited by technical sources of dephasing rather than some fundamental property of the qubit itself. Trapped ions also benefit from the fact that all of the ions of the species are exactly identical, right? That's not true of solid-state systems. That's not true, for example, of NV centers. That's not true of molecules. That's not true of lots of other systems. So trapped, like every ion is exactly the same. The other thing is that while any ion contains maybe additional states beyond the ground state and the excited state that you're specifically pumping, the states are kind of finite. There's not so many of them. And so performing quantum operations is pretty straightforward without having interference from transitions between or among these other states. You can trap ions for many hours, or in some cases up to months if you're using really heavy ions, so that's why they often choose pretty beefy ions like calcium and barium and rubidium and things like that. And the big disadvantages are, while in principle it's easy to trap larger and larger numbers of ions, in practice scaling is really, really challenging. I think that's the biggest thing that needs to be overcome. Arrays of up to thousands of trapped ions have been achieved by D-Wave, but these typically have very short coherence times and they haven't been used in any meaningful way. So most trapped ion systems involve just a few ions, and the ions are not productively entangled. So you can kind of trap and manipulate single qubits, but actually getting the whole state, the whole system to behave as a single entity through entanglement is very, very challenging. You need many lasers, obviously, because each ion needs at least 2 lasers to manipulate. So they're pretty complex systems. They're also usually enormous because of all this machinery that's required, and so there's a lot of emphasis on moving to sort of microchip style trapped ion systems. At the beginning of next class, I think what we'll do is we'll talk, just kind of speed through the last few qubit platforms, spin qubits, photonic qubits. I had my homage to the Nobel Prize today, but we'll just do it next class because I want it to make sense, and it's going to make sense.